All right, welcome everyone. Thanks for sticking with us while everyone finds this through this maze building. Welcome to Harvard's Science and News lecture series. How many of you guys have been to one of our lectures before? I see some familiar faces.
Welcome back.
How many of you is this your first Science and News lecture? Oh, awesome! That's what we like to see. So we are members of Science in the News, which is a graduate student organization or club on Harvard's campus. And we kind of have two primary goals in all the work we do. We want to talk about cool science with the public, non-scientists, and interested people like yourselves. And also we want to train ourselves and our fellow graduate students to be better communicators of that science. So we do a bunch of different things. We have lectures like the one you're going to see tonight, which is put on entirely by graduate students, and a lot of grad students behind the scenes who work with them to make sure that their lecture's really good, their slides are really beautiful, they make the graphics. So there's a lot of people who put work into this event. We also have a really great blog, which is on our website that you can find on the handouts or the flyers. And we write both short little pieces about stuff in the news and also longer pieces about interesting science that our grad students want to write about. We have a science cafe targeted towards the older crowd called Science by the Pint, where we bring a whole lab to a bar and you can have more of a one-on-one conversation about the science rather than a formal lecture. And we do lots of other stuff. We have some school outreach. We have a day-long conference that we hold in summer. If you want to get more in-depth into a single topic. So yeah, grab some of our flyers, check our website out, follow us on social media, and we hope to see you at some future lectures.
Okay, so tonight we have three great speakers who are going to be talking about their voyage to discover sources of cosmic signals in our universe. So their lecture will be split into three parts, and we ask you to hold your questions until they stop for a question break. After the second section, we're going to have a short intermission for about 5 to 10 minutes. You can grab some snacks, use the restroom, and then be back here for the last part. And then after that, they are going to give a couple of really cool demos about space. So if you would like to stick around for that, just come down to the front of the lecture hall at the very end. And we also ask that before you leave, you fill out one of our audience surveys. There's a few on the table out there by the snacks. We really look through those to get ideas about future topics. If there's anything you want to learn about, write it down. If there's anything that we could do to improve this series or that the speakers could do to improve their lecture giving abilities, we would love to hear that. So with that, I think we'll let our first speaker take it away.
All right.
Okay, so can you hear me? First of all? Okay. So good evening, everyone. Welcome to this Science and News lecture. In order to start our voyage to discover the cosmic signals in our universe, I want to show this photoplay video.
Ladies and gentlemen, we have detected gravitational waves. We did it.
So what you just saw is the announcement of the first detection of gravitational waves in 2016, just a couple of years ago. And some of you might have already heard of it, but like, aren't you excited? Okay. Maybe one question that some of you might have had so far is, what is a gravitational wave? And then what happened in the last 2 years is that if you look into the astrophysical articles or newspapers, some of you might have heard of like the gravitational waves, pictures of black holes, you might have heard of lasers, you might have heard of neutron stars collisions, and the end of multi-messenger astronomy, like a lot of technical terms.
So we're living in a very exciting time where we have this new technology and instruments such as radio telescope, optical telescope, and interferometry. And with these new technologies, we're able to make new groundbreaking discoveries in astronomy. And have you ever wondered what do these discoveries tell us about fundamental physics and our universe? And why are scientists so excited about these new discoveries? So today we'll be addressing some of the questions to you. And Nicolo is going to tell you about neutron stars and how do neutron stars tell us about the origin of heavy elements. And I'll be telling you about black holes and answer questions such as where does information go inside of a black hole? And does it disappear? And Nick is going to tell you about quasars and explore the connection between fundamental physics and quasars. So together we're going to go on a voyage to explore some of the most mysterious and exotic objects in our universe, and explore some of the sources of the cosmic signals that we detected in the past couple of years. So without further delay, let me leave the stage to Nicolo and let him tell us about neutron stars.
Yeah. Sorry, we have a really awkward tech setup. The people watching the live stream, I'm sure.
Yeah. You have one more.
Not.
Should be okay. So, okay. So to talk about neutron stars, I want to start from like our feature of our newspapers articles, and I want to point out that okay. Okay. I want to point out the two of them were like about neutron stars and particularly neutron stars colliding. So today I hope like I will be able to give you an idea of like what this neutron star collision event was and yeah, try to understand how it's affecting and what does this imply for our knowledge of the universe. So indeed, we're gonna try to understand what are neutron stars and like how we can detect them and what we learn from them. So in order to start about this topic, I want to go back, doing one step back and go to what is a star. So a star is in general a massive bright object that emits light, and this light is actually produced inside the object somehow. And we're actually very familiar with stars because the sun that we see every day is one very good example. But also, if we look at the sky during one clear night, probably not in Boston, we'll be able to see a lot of these white dots. So all of them are stars inside our galaxy. But we also have some false signals that are bright, but they're not bright because they produce light. They're bright because they reflect light. So for instance, the moon, or even Mars, that you might see in certain conditions like during lunar eclipse. And it's actually a planet that reflects light. So there are in general many different types of stars. This is like a non-complete catalog. Some of them are brighter, some of them are bigger, some of them are smaller. But just to give you an idea, like the sun is a pretty typical example, and it's one of the most common that you can find in the universe. Neutron stars are actually a bit more exotic, and they are more or less the smallest stars we can find in the universe. So usual types of stars, like the sun. So let's have a recap on how a star works. So a star works is a giant ball of hot gas, and when you have something that is very hot, it starts emitting light. And this is the way basically the sun works. So when you have hot things, they emit light, and when you have something hot that emits light, like an example that you might be familiar with is like iron. When you're metal, when it's very, very hot and it's liquid, it starts glowing with the light. So this is exactly the same mechanism. So now we want to go from our usual star, the sun, to a neutron star. In order to do this connection, imagine to take the sun, whose radius is about 700,000 kilometers, and try to compress down, imagine for a clamp, and compress it down to something that is wide 10 kilometers. So in this way, you get your neutron star. Just to give you an idea of what this analogy means, imagine that you want to build a neutron USB port. You will need to compress the Eiffel Tower to the dimension of the USB port. So this is the analogy to give you the idea of what difference in size we have. In general, this mechanism happened through something that is called supernova. And just this is something important for what I'm going to tell you about later. When you have a very massive star at the end of its life, typically undergoes a process that is violent compression, and we call it supernova because it produces a lot of light. And after this, in the remnant, you get a neutron star. And since you have compressed something down to such scale, the matter is so dense that it's made of neutrons, and this is the reason why we call it a neutron star. So, in general, neutron stars are kind of interesting in exotic objects, and I will play this small video to explain you a couple of features of these stars. So they are typically spinning, as it is shown here. They have a strong magnetic field, that is something that is emphasized by these magnetic field lines. And also, as you can see, this green jet is basically an emission of light that happens through this very focused jet. So we're going to see the properties in detail. So, as I said, there are very extreme conditions that we're gonna try to understand. They have very large density. They actually the strongest magnetic field you can find in the universe. They're also spinning at very extreme speed. In general, they are no conventional star because they emit light in a kind of interesting way. We said that they are very, very dense. They're much denser than whatever you can imagine to do on the Earth. And to give you an example, imagine you want to play bowling on a neutron star. Okay, so you better start training now because a bowling ball weighs weigh as much as 100 Empire State Buildings. But now, you suppose you are interested in understanding the magnetic field of these neutron stars, and so you're familiar with magnetic field when you think of fridge magnets, and in general, a fridge magnet has a magnetic field of the order of 100 Gauss. So what does this mean? Doesn't matter too much. A neutron star magnetic field is about 1 trillion Gauss. So of course, this number doesn't mean so much, but you can see there's a 10 million difference between the two numbers. So now suppose you want a neutron star fridge, and you want to pull off one of these magnets from the fridge. Okay, so if you were to do on your fridge at home, it's pretty easy, right? It doesn't require much force. If you want to do on a neutron star, probably it's better if you use a truck and you attach it to the magnet and you try to pull it. But probably one is not enough. And better if you use 1,000 of them. Yeah. So as I said, neutron stars are also spinning at very fast pace. When you want to understand when an object spins, a usual good quantity is the duration of the day somehow. So on the Earth, the duration of the day is the time required for the Earth to complete one turn. Okay. So the neutron star, if you compare the day of the neutron star, would be 1 millionth of the day of the Earth. So 1 day of the Earth is 1 million days of the neutron star. And when you have a spinning object, if you're sitting on this object, you will move with this tangential speed. And if you are on the Earth, this tangential speed would be about 1,600 kilometers per hour. Okay, suppose now you are on you are on a neutron star, this would be 2 million kilometers per hour. And this is much faster than whatever we ever built on the Earth. So now let's go to try to understand how we can actually observe these neutron stars. And we basically have two ways so far. The first one is using light, and so we are trying to address in which sense neutron stars are actually stars. So which sense they emit light. And secondly, using gravitational waves. And this is something very new, it's something that came up last year. And we will try to understand how we can have neutron stars emitting gravitational waves. So neutron stars are non-conventional stars. So let's go back to our conventional star, the Sun, our favorite friend. So in general, when you have like a standard star, it emits light in all directions. So it's like a perfect sphere and flashes all around. But if you have a neutron star, as we saw in our previous video, what do we see? So we see that there is a kind of jet of light, this green jet of light, that is very focused and is spinning around together with the neutron star. Okay, so the light emission happens mainly in this small cone, and this cone is spinning around. So, yeah. So to recap, we have only one direction. This is actually the direction of the magnetic field. It's not random direction, and it produces a kind of jet of light, and the jet of light spins together with the neutron star. So imagine now we are on the Earth. How would we see this neutron star? And in general, neutron stars are like similar to lighthouses. So they spin, and whenever the flash of light passes in front of us, we see a blink of light. Okay, so we have our beautiful lighthouse to build our example, and then our detector records the intensity of the light as a function of the time. Okay, so what would we see? We would see some peaks happening at certain times with a certain period. And for this reason, these objects have been called pulsars at the beginning because light comes in pulses. So the first observation was made in the 60s by Anthony Irish and Jocelyn Barnell. And this is actually the data collected. And to show you that data can be not so difficult, this is actually pretty close to what we see before. If you look like in detail, you can see these small peaks. On this axis, you have 0 seconds, 10 seconds, 20 seconds. You see exactly the same pattern. So they look for like these pulses, they saw them, and they understood it was a neutron star that was like spinning around and flashing towards here. Since it was an important discovery, it led to a Nobel Prize. Before going to a new, slightly different topic, I'd be happy to take any question you might have so far. Okay, so there is.
What process makes to make a star to become a pulsar or a neutron star? What process makes it to compress so much? Okay,
so the question is, what process transforms an orbital star into a neutron star? So basically, when you have a star close to the end of its life, it means that there is no. So usually in a star you have nuclear reactions happening in the core, and at one point there is no fuel for this reaction. So when there is no fuel, there is nothing that can avoid the star to compress, because gravity wants to compress the star down. And so there is nothing, the star starts collapsing, and this collapse is so fast and so violent that in the end, you reach a point in which the matter is so dense that it can balance gravity. It's a violent compression due to the gravity of the whole star.
Then the neutron star is a old star.
It's like the remnant of a big giant star. Yeah.
How hot is the neutron star?
So the question was, how hot is the neutron star? Well, neutron stars are typically pretty hot at the beginning, because imagine you have a big star, so like the sun, or like usually something bigger than the sun, then this compresses down, so like the temperature still stays hot. So the surface of the sun is like maybe thousands of degrees Kelvin, and so it's still hot, but it actually cools down through time, like in millions of years, and some of those that we see are actually very cold, much colder. Yeah, so I think it was good.
Right. Is there a limit to the mass of a star that I'm about? Is there upper limit to the mass of the star?
Of a normal star, I mean,
right, the big star, how big can it be?
Well, I don't think there is actually an actual like limit. But usually, like the bigger the star, the more massive the star, the shorter their lives. So when you form like very big stars, they don't last for long. So you will not have time to observe typically. Like you just
specific limit as to how big, how massive the star can be.
Not very
Well, as far as the mass is concerned, it can be any number or just some discrete numbers compared with solar mass?
No, of course, it can be a continuous number. So the question was if there is a continuous or discrete number in respect to solar masses. No, it's typically no, it can be a continuous number in general. It's hard to find stars that are more than several tens or hundreds solar masses, because as I said, they live very short and they disappear immediately. So we don't have the time to see the sky.
And so to add on to that, I guess when a star becomes too massive, it becomes something else.
Yeah.
Cool.
Okay. Yeah, I guess it's you.
Hi, since neutron stars are released of like old stars and they don't emit as much light over millions of years, can you still see? You can only see them through a telescope, or can you actually see them
by eye?
Yeah.
No, they are like they are very small. So the intensity of an object. So wait, so the question was if you can see by eye,
or by can you see them by just a regular telescope and not something as powerful as telescope?
No, yeah, okay. If you can see them by eye through a telescope. And the point is that they actually, if you look at with a normal visible telescope, they are not super bright because they are pretty small, so they can still light disproportionate to the surface. And indeed, like the main mechanism for them to emit light is something like this, so you need a specific telescope to observe such radiation. Okay. Yeah.
The pulsing from the light, I understand that the neutron star is spinning on its magnetic axis, and that's creating a directional beam of light on its axis. But is it also tumbling, which is the, so that we would visually see the axis or be on axis with its axis? Is that why we see a pulse? I don't quite understand, because if it's spinning and we are off axis of that, we would see no light, correct?
Yeah, the question is what happens if like the neutron star is spinning and we are off axis with respect to the neutron star. And the point is that indeed, like there are probably many neutron stars that we not observe because the beam of light hasn't hit her. Yeah, because if you have like if this is like the rotation axis and this is the beam of light, it's like this. But if the Earth is there, like the beam of light will never touch here, so you can observe it. Yeah, I think it was over there before. Yeah.
I have two questions. One question is, I think of light being from an electron going from an excited state to a lower state, and the difference in energy is becomes the energy that is the energy of light. But in a star, the process is fusion, which is orders of magnitude greater in energy than the difference between energy levels in an atom. So where does the light come from? Since it seems like it's not coming from an electron going from an excited state to a lower state. And the second question is, if a neutron star is made of neutrons and it comes from a collapse of the star, does that collapse involve the protons and the electrons being ejected, and how does that happen?
Okay, so there were two questions. So we repeat the first one is that if for a star, like which kind of radiation do you have from a star with respect to the radiation called as photons emitted when an electron passes between two energy levels in an atom? And the answer is that for like in general, for a normal star like the sun, the radiation we see, the light we see is from thermal radiation. So it's just because when you have a hot body, it emits light. It's not an electron transition between two levels. And what happens inside the core is that you have nuclear reactions. They produce a lot of energy. This energy like propagates through the external layers of the star and makes them hot. And this energy is then released in a different way. So like the core is heating the star, and then the emission of light happens from the external layer as thermal radiation. Does it answer the question? And the second question was, since a neutron star is made of neutrons, so like does this process of creating a neutron star involve electrons and protons somehow? And the answer is yes. So when you have this violent process, you can, at one point, having collisions between protons and electrons that are so hard that they merge into a neutron. And actually, this process produces a new particle that is called a neutrino, and neutrino escape. So the inverse process of splitting a neutron into protons and electrons cannot happen. And this is basically why you end up with just a neutron star, with just neutrons.
So I think we'll let the next speaker, and then if you have more questions, we can ask them at the break or at the end.
Yeah, so just to emphasize a point that maybe was not clear, the two mechanisms to emit light between a neutron star and the normal star are fundamentally different. So one is thermal radiation, the other one is through this jet of light. And you will see this mechanism of emitting particles to eject later on again. Okay, so now I want to go to my second part that is about neutron star merger. And I want to show you a video of what happened in 2017 last year. So as you might have guessed from the music, it was a very Okay, so what did you see? In August 17, 2017, a neutron star emerged and is detected by LIGO from gravitational waves and by Fermi telescope, ESO, other probably about 70 telescopes through different kind of light. So this is the actual result, but what does all this mean and what does the video mean? Okay, so we're gonna go now to try to understand the first part of the video when we have two objects that are spiralizing together, one against each other. At one point they merge and they produce a new object and a lot of light is emitted. This is more or less what we saw. So let's try to go back and understand the first part. And the first part, gravitational waves are emitted. And so let's go back and try to recap gravity. So gravity is in general like the force that binds massive objects together. And for instance, one example is you and the Earth, you experience gravity every time, but this guy is experiencing gravity because it jumps, but it will again fall down to the Earth. Then also gravity is what keeps the moon orbiting around the Earth orbiting around the sun. So it's really the same load that is applied to different levels. But in general, the important point is that the larger the mass is, the larger the force is. So gravity is very important when you have very massive objects. So now let's try to understand what happens when you have massive objects that move fast and accelerate. And in general, they form like perturbations. And these perturbations propagate as waves, exactly the same that happens when you throw like a stone into a lake and you see like waves forming and propagating to the lake. But if you have one object alone, this will not move because there is nothing that can accept force on that. So you won't have any gravitational waves because you need something that accelerates and move fast. But if you have two objects, they can pull each other, and when pulling each other, they accelerate so fast they can emit gravitational waves. So for this reason, we needed the neutron-star merger. It's something that we be able to see only last year to observe gravitational waves from neutron stars. So in general, the second concept we need is the fact that when you have two things colliding, you can produce light. And in general, think if you have two billiard balls and you throw them at very high energy, what can happen is that you break them down and you produce a lot of fragments, right? So in general, in a collision, you have often like a lot of energy that is involved. When you have a lot of energy, again, we go back to like our thermal radiation from the sun, you can emit light, more or less a similar concept. So like we get two objects colliding very fast, a lot of energy, we produce a lot of light. So now that we understand this concept, we can watch the video without music, trying to explain what we see. So now we see a moment in which two neutron stars are spiralizing together. In this moment, they are emitting a lot of gravitational waves. And after a few seconds, you see a collision, and a lot of energy is emitted in form of light. That are like these bars of light you can see from the video. So yeah, two important steps: spiralizing, gravitational waves, collision, light. Okay, so detecting the neutron star structure. How did this happen? Pretty straightforward now that you know all these things. So two neutron stars produce gravitational waves. Okay, it was detected, and was detected because the technology to detect gravitational waves, such signals, is very new, and such telescopes like LIGO and Virgo detected those signals. But then we had additional signals coming from light, and there are several telescopes, both on the Earth and in the sky, that detected this light. And this is it is very exciting because it's the first astrophysical event that was detected with two fundamentally different types of signals at the same time. And this is what we call multi-messenger astronomy, because we saw a certain astrophysical event with two different signals, completely fundamentally different. So, eventually, what do we learn from neutron stars, apart to understand like all these cool things happening in the universe? They help up answering the question, where do all the elements come from? So the first question is, what are the elements? And the elements are all these little boxes in the periodic table of elements. So like we know that matter is organized in different kinds of atoms. Each atom has a different name. Okay, and so the question is, where do all these elements come from? Okay, so in general they come from stars, and stars are somehow the forges of our universe, because thanks to the nuclear reactions we were discussing before, they produce new elements. And so let's try to understand a bit better this. So stars are in general hot, and they emit light because they are hot. So this is what we have seen so far. So, but why they are hot? Because there are nuclear reactions happening inside their core, and this nuclear reaction produces elements such as carbon, nitrogen, oxygen, all the elements you are familiar with, but the process stops at the iron. So the question is, where do heavy elements come from? And now I want to give you this concept of light elements and heavy elements. And more or less, we call light elements all the elements that are at the beginning of the table that are somehow lighter until the iron. And we know these elements, for instance, they are the one important for life, for instance, carbon and oxygen. We know they are produced inside normal stars. Then we have also heavy elements, and these heavy elements, well, we usually use those. For instance, tungsten was used for light bulbs, but also gold is a very interesting element that we've been using for years. And actually, those are related to neutron stars. So, why neutron stars? Well, go back to the process in which we form neutron stars. We said we have a compression of a star to something about 10 kilometers wide. Okay, and this is actually a very violent process, and this is what we call the supernova. So, in this mechanism, you imagine that you have very, very strong collisions among particles. And these so strong collisions can produce like heavy elements. You can actually merge two atoms to produce a new heavier atom. This is what happens. Unfortunately, this is not the end of the story. It is not the end of the story because supernovae are not enough to explain the abundance of heavy elements that we see in the sky, that we see in the sky, or that we observe on the Earth, for instance. So, like, suppose you watch the sky and you count how many supernovae you see. Okay, then you say, okay, I know how much gold is produced for each supernova, and then I multiply by the fact by how many supernovae I see in the sky, and this is how much gold I should observe in the sky. But actually, what I observe is much more. And so, where does this excess come from? We have the answer. We have the answer thanks to the event we observed last year about neutron star mergers, because also neutron star mergers are very, very, very violent processes. You can have strong collisions among particles, and these collisions can produce heavy elements. So supernova by itself is not enough, but if we add neutron star mergers that we just observed, this is enough. So this brings to my conclusion and recap. So what we learned so far today is that neutron stars are actually extreme stars. We learned that they're very dense, that they have a very large magnetic field, and that they are spinning at a very fast pace. We also learned that they emit light in a non-standard way because it's mainly focused in one direction, and it's detecting impulses when we actually want to detect those. In general, they're responsible for the presence of heavy elements in the universe, and we know that supernovae produce heavy elements. This is actually not enough, it's not the end of the story. Also, neutron star mergers produce heavy elements, and together these two processes help us understanding where the gold comes from. Thank you. So yeah, got any few questions for at the end of the paper? Okay.
Hi. So you said that neutron stars are called neutrons because when the electrons and protons merge, so they become just neutrons, right? Yeah. So, but you also said that this collision, this merge, in which the neutrons are created, they also create elements, light and heavy. So elements, regardless of the weight, are made of neutrons, protons, and electrons. So if there's only neutrons in a neutron star, so So how they create elements?
Okay, thanks for the question. So, like the question was, how do you reconcile these two facts? The first one is that the electron, when you form neutron stars, you have electron and protons merging to create neutrons. On the other hand, you have elements merging to create heavier elements. So the way we reconcile these two is that in this violent process, it happens like if you want in different steps, you have collisions between two atoms, and they create new atoms that are heavier. So this is the way we create the heavy elements. The second one is that when at one point the compression is going at a point in which the matter is so dense, you start like somehow disrupting the atoms, and at one point you have the density is so large that electrons and nuclei are more or less in the same space, and so you have these collisions between electrons and protons that create neutrons. So it's actually a more complex process than like just these two different steps.
So what I can see is that before the final step in which the neutron star is created, just before that, elements are created.
Yeah, that's correct. It happens like before. So like in the very core, you create the neutron stars. In the rest, you have all these heavy elements.
Thank you.
Yeah.
How long does it take? Like, you know, in the video, it takes what, 15 seconds or something. But are they? I think you use the term spiralizing.
Yeah.
How long are they spiralizing?
So the question was how long the neutron stars are spiralizing for, and it's actually like you should imagine that this spiralizing actually started very long time ago and was very slow. But then when they get closer and closer, it becomes faster and faster. And we can observe with our detectors only the last part of the spiralizing. And actually for neutron stars was tens of seconds and can be up to hundreds of seconds. You can actually really observe the spiralizing for long. Maybe, yeah.
If you really tried, could you compress the neutron star farther?
So the question was, if you could try, could you somehow compress the neutron star farther than that? And somehow yes, and indeed, if the star is very massive, after this compression, instead of ending up with a neutron star, you end up with a kind of different object that is a black hole, and you will probably learn about black holes pretty soon. And maybe, okay. So I'll leave the floor for the next speaker. So Zoe will talk about black holes and try to understand where does information go when it gets to a black hole. And I'll be happy to take more questions afterwards, and even like I'll stick around after the presentation.
Okay. Good evening. My name is Andrew, and I'm a second-year graduate student at Harvard University in the physics department, and my research field is theoretical condensed matter physics. And today I'll be telling you about black holes, and this is the second stop of our space journey. So I'm going to begin with this clip of the newspaper article. So 100 years ago, Einstein predicted in general relativity that the shape of a black hole should be a ring. However, we haven't directly observed any black holes yet. So this newspaper article is about the recent effort of taking a direct image of a black hole. And so today I will be telling you about what we already know about black holes and what we don't care about black So I'm going to begin with what is a black hole, and then I'm going to briefly tell you about what we know about what black holes should look like. And I will also answer the question if we can actually observe a black hole. And lastly, I'm going to tell you where does information go inside a black hole. So what is a black hole? This is an artist's interpretation of a black hole. And we probably know from science fiction, novels, or movies that black hole is something that traps light. And this is actually a reasonable thing to think of. So our formal definition of black hole is that it's a region in space with very strong gravitational effects that nothing, not even light, could escape from its inside. So let's break down this definition a little further. Let's take a look at some parts of this definition. So a black hole has a very strong gravitational effect. And as Nicolo told us about gravity, if you throw a ball into the sky, the ball is going to drop to the ground due to gravity. And this is also the same force that keeps the planet's orbit around our sun. And black hole is taking this to an extreme. It has very strong gravitational effects. And due to this gravity, light cannot escape from its inside. So to understand this better, let's consider an ordinary matter. So anything that surrounds us. If we shine a light into an ordinary matter, the light is going to be reflected. And this is why we see colors. And for example, this is an ordinary matter. It's called a cloud gate. It's a big like sculpture in the city of Chicago. So if you're like Nicolo, when you visit the cloud gate, you look into the cloud gate, you're going to see yourself. And the reason is because of the reflection of the light. However, this is not the case for a black hole. If you shine a light into a black hole, it's gonna spiral around the black hole, follow some curved trajectory, just like when you're throwing a ball into the sky. And the thing is, the light is not going to come out ever again. So this is a black hole. And then how do we describe a black hole? And it turns out that to fully characterize any astrophysical black hole, we only need two things. And the first thing we need to know is the black hole mass. And the second thing we need to know is the black hole spin. So by these two standards, the types of black holes are stellar mass black holes, supermassive black holes, spinning black hole, and spinless black holes. So first, let's look at the mass of black holes. And there are two types. The lighter types we call a stellar mass black hole. They weigh few solar masses, and the solar mass is the mass of our sun. And we believe that they form from collapses of the star, just like what Nicolo just told us about neutron stars. So when they become more dense, they become a black hole. And they're actually not that real in our space. There are hundreds of millions of them in our own Milky Way galaxy. And the second type is called a supermassive black hole. And their mass can span from hundreds to billions of solar masses. So where do you find them? Here is a picture taken in the center of our Milky Way galaxy. So behind this bright cloud, there is actually a supermassive black hole hiding behind. So this is the Sagittarius A star black hole located in the center of our Milky Way galaxy. And another example is M87. It is the supermassive black hole located in the elliptical galaxy Virgo A galaxy. And this is the second nearest supermassive black hole from us. And so how heavy do they weigh? For example, the mass of Sagittarius A star is 4 million solar masses. And what does this mean? So if our sun weighs as much as a golf ball, then a Sagittarius A star would weigh as much as 30 elephants. So it's really massive. And the second standard to describe a black hole is its spin. So this means whether the black hole is rotating or not. If the black hole is not rotating, it's a spinless black hole. It's also called the short scale black hole. And if the black hole is rotating around itself, we call it a spinning black hole or a curved black hole. And M87 and Sagittarius A star, the two supermassive black holes that I just told you, are both spinning black holes or curved black holes. So what does a black hole actually look like? I just told you that we haven't directly observed any black hole yet, but we have some idea of what they should look like based on Einstein's theory. So here is a numerical simulation of a black hole. Of Sagittarius A star, this is the supermassive black hole of our own galaxy. So if we stare at this picture, we would see a few striking features. And the first thing we notice is probably this black region in the center. And so you notice there's a boundary. We call this boundary to be the event horizon telescope. And this is the limit beyond which no matter can escape from. And the second thing you will probably notice is this light ring-like structure surrounding this dark region. And we call this the accretion disk. And this is forming from matter slowly falling into the black hole. And they're highly energetic, and because when they're spiralizing and falling into the black hole, this process takes a very long time. And as Nicolo just told us, very energetic matters would have very emit light, and therefore they're very bright. And this is what we would observe if we were to look at them. And Nick is going to tell you a little more about accretion disk later as well. So the third feature was not obvious in the previous picture, but let's look at the black hole from a different angle. So this is the side view of the same black hole, Sagittarius A star. We can see some light beams shooting directly out of the black hole, and we call these jets. And similarly, we also saw that in the neutron star. So these jets are also very energetic. For example, the jet of an M87 black hole stands as long as 5,000 light years. That means we can travel from the Earth to the Sun 200 million times. So this is a really long and bright jet. So we don't exactly know what fueled them. So this is an ongoing research area, and there are two possible theories. And the first one is accretion disk might fuel them. And the second one, the second mechanism is the black hole itself can possibly fuel them when they're rotating. So a question you might be wondering is that if we haven't observed a black hole, can we possibly observe an actual black hole? Well, luckily the answer is yes. So the Event Horizon Telescope is an international collaboration that aims to take the first direct image of a black hole. And the targets are the two supermassive black holes that I just told you. The first one is the Sagittarius A star. It is 25,000 light years away from us. And M87 is located 15 million light years away from us. The way we do that is the very long baseline interferometry, which I will tell you a little more later. So to take a picture of this telescope, it's very challenging because they're so far away from us. And so to do that, we can imagine we need to see them very well. And intuitively, we understand that the larger of a telescope is, the better we would be able to see. Indeed, that's the case. So Event Horizon Telescope is essentially using the entire Earth as a telescope. So we have a huge telescope, and so we will be able to see them, see the black hole better. And to be able to see a black hole, we needed something called good resolution. So to give you an example, the picture on the left has very poor resolution. So the image is very blurry, we can't really see the details. But if we have a good resolution, then we will be able to see the detail of the image. But in reality, when we're taking an image of a black hole, we don't have that much of a good resolution. But to be able to see it, we at least need something that's comparable to the size of the black hole. So our resolution is 20 microarc second. So what does this number mean? A microarc second is 1 millionth of an arc second. And an arc second is 1/60 of a degree. So what did this number actually mean? So this is saying that we will be able to read a newspaper article from New York City in LA. And this also means if there's an orange on the moon, we'll be able to see it from the Earth. So that means our resolution is really good with this telescope. Well, how does this work? Let's maybe consider a simple example of two telescope disks. And these two telescope disks are facing the same direction and directly towards our target black hole. And they're located at different positions on the Earth. So because of their different locations, the signals from the black hole is going to arrive at these two different telescopes at different times. And to see this, for example, if I stand here, I throw a ball and Nicolo or Nick, the ball is going to arrive at them at different times. And this makes sense. And so for a black hole, there is also a time delay between the signals arriving at telescope A and telescope B. And it turns out that if we measure, this time delay would actually tell us about the source that we are looking at. And then we measure this time delay and we obtain one data point on our black hole image. So the Event Horizon Telescope has telescopes all around the world, from Hawaii to the South Pole. And by using those telescope size, each pair of them would give us one data point on the images. And then as the Earth is rotating overnight, we will have multiple data points on the image. So the figure on the right is telling you the measurements we have on the image plan. However, you might still wonder, we still don't have all the data points on the image. So how do we reproduce the image with so many data points missing? And to see that, I'm going to play you a video clip and explain this how it works. So I'm going to play it and let you try to identify what this music is. And yeah, to see if you will be able to tell what the sound is before the end. Okay. So you might be able to identify the music before it ends, before we include all the notes from the keyboards. So that's exactly how the Event Horizon Telescope works. So if we consider our measurements, each measurement as each note on the keyboard, we don't actually need all the data points on the image to be able to identify the image. So if we take our measurements, there are actually infinite number of possibilities that could fit to the measurements. However, not all images are created equal. Some images are more likely than the others. So what we were trying to find is the most likely image that could fit our measurements. So then we would have our network of telescopes to start with. We take our measurements. We don't have all the data points, but just like we don't have all the notes from the music clip, we are still able to reconstruct the image or reconstruct the original music. So now I want to bring to your attention that Event Horizon Telescope is an international collaboration and an effort across different fields. So it has telescope sites in different countries, in the US, in Mexico, in Spain, and in the South Pole, in Greenland. And it also combines with efforts with people from different fields. For example, computer scientists are working on image reconstruction, and physicists and astrophysicists are working on the theory side of things and explore the general relativity and the shape of actual black hole. And there's also engineers and technical support that makes observations at different telescope sets possible. So it is with these collaboration and the combination with different talents that makes this exciting project possible. So even though you might not consider yourself as a physicist, there is still a way that you can make a contribution to astronomy or the field of astrophysics. So now let's step back and look at our definition of a black hole. So we said in the beginning that black hole is something with strong gravity and nothing can escape from its inside. However, there's a problem with this definition. And to see where the problem comes from, let's look at some basic physics law. So we know in physics that conservation law is something that is universal. And what does this mean is that the total amount of matter or information in isolated system stays constant over time, such that isolated system can be our universe. So if you have a cookie in a box, if you wait long enough time, is it going to become 7 cookies? Very likely no. Actually, no. This is not going to happen. Instead, no matter how long you wait, you will still get 1 cookie. So this is a statement of conservation law in physics, and this is universal. So for black hole, this is kind of problematic because we just said nothing can escape from the black hole. Then where does information go? So do they disappear in a black hole? And that would mean conservation law is violated. So this is problematic. So it turns out the proposed solution to this is that the black hole is not so black after all. So in 1974, Stephen Hawking proposed the idea of Hawking radiation, or the so-called black hole evaporation. And the basic idea is that he thinks information can emerge from the event horizon of a telescope, and then black hole can, in this way, give out information. And so because black hole is giving out information, the mass of black hole would actually decrease over time. So that means the black hole would eventually disappear. So this is why it's called the black hole evaporation. And in 2004, Hawking claims that black hole evaporation or the Hawking radiation can solve the black hole information paradox, because the matter does not emerge from the event horizon from nowhere. It's actually coming from the matter falling into the black hole initially. So conservation law is not violated. However, this has not been detected. Our ongoing effort to detect Hawking radiation includes Fermi Space Telescope, and it's detecting the light or radiation coming out of a black hole. So to recap, I've told you the definition of a black hole. A black hole is something with very strong gravity, and nothing can escape from the black hole, the inside of the black hole. And I will also tell you about, to fully characterize any astrophysical black hole, you only need to know the spin and mass. And I introduced the effort to take the first direct image of a black hole, the Event Horizon Telescope. And I also told you about the black hole information paradox is the contradiction between the definition of black hole and the conservation law. And our proposed solution is the black hole evaporation. And with that, I'm happy to take questions. Yeah.
Right. So you said the stellar mass black holes and supermassive black hole. What happens in between those two ends? There's no limitation as to the mass of the sun, right? So presumably there can be the distribution of mass.
Yeah. So there's no really hard boundary between these two types of black holes. So the reason why we classify the black hole like this is because we know that supermassive black hole exists in the center of a massive galaxy. So it's mostly where they are located and their origins. We understand stellar massive black holes relatively well because they come from collapsing of stars. Just because your neutron stars become so dense, so the gravity becomes so strong, it becomes a black hole. But for a supermassive black hole, it's not as well understood.
But in theory, it continues.
Yeah, in theory, there can be continuous in between. Yeah, there's no really boundary. Yes.
Shouldn't it be called the light or the bright hole because like it emits a lot of light?
Okay, so the question is if black hole is so bright, why is it not called bright hole? So the reason is because it has an event horizon. So the black hole itself is actually dark. It's very dark because nothing can really escape from the black hole. And I just told you about the black hole evaporation. That radiation is actually very weak compared to the accretion disk. So if you're thinking about the light ring around the black hole, that is actually not a part of the black hole. It's more like the matters slowly falling into the black hole. Yeah, so black hole is still pretty black, our center. Yeah.
So the information, the Hawking radiation information that's coming out of the black hole here, what would it be? Would it still be light?
Yeah, so the question was, what would the Hawking radiation be? Would it be light or what is it? So we know that anything with finite temperature would emit radiation or light. So the black hole radiation is actually a consequence of prediction by Hawking saying that black hole is not doesn't have zero temperature. It has some very small finite temperature. And because of this finite temperature, it's going to radiate out some heat, although it's not very hot. Yeah, so it's still thermal radiation. Yeah.
So I have 2 questions. You mentioned about astrophysics. So my question is, there's such a thing as astrochemistry?
Mm-hmm.
There is?
Yeah.
Oh, okay, good, thanks.
Yeah, there is astrochemistry actually. So, well, the question was if there's anything called astrochemistry. Yes, and the answer is yes. There are actually professors at Harvard University in the astronomy department working in astrochemistry.
Okay, thanks. The second question is, so in the process of creating a neutron star, so elements are created. After that, so just neutrons remain. But beyond, when the pressures go beyond neutrons, is what creates a black hole. So my question is, so what since black holes seems to be made from something other than atoms, what black holes are made of?
So the question was, what if the collapse of stars form neutron stars? What are black holes made of? So my answer to this question is that we know that the collapse of stars form stellar mass black holes. By the same mechanism forming neutron stars, stellar mass black holes are made of. So I guess their compositions would be the same as a neutron star, if you agree.
Yeah, maybe something I can try to add is that we don't know what's inside a black hole. We cannot look in there because nothing can escape from that. And if you take like very general relativity, the prediction is that everything falls at the center of the black hole, and we don't have any possible clear description. So we just know that the matter that is inside the star falls into the black hole, so it's there, but we don't know which form it has.
Yeah, so everything is all of our current understanding of the black hole is only theoretical study. We definitely know the black holes are there. We have direct evidence, but we haven't observed a black hole yet. So we don't know the shape of a black hole, and we don't know their compositions exactly, and we don't really know what they look like. So this is a part of ongoing research area.
Yeah, so I think we're going to stop for about 5 minutes for a short intermission. If you have more questions, you can come down and ask them during the break. Stop.
I'll bring my stuff. Do you have one? Thank you.
It's necessary for them to speak in a way that's informational, but it doesn't after the seminar last year, she was and I told her next time there's an event that there was a fair amount of time before I see one advertising. But I told her whenever I see one advertising next to
Yeah, I mean, we don't know if there's
she wasn't familiar with
so there might be something out there. Yeah.
Well, I asked her.
Yeah, that's great. Because we actually have some students who are kind of near
But yeah, it's
but we don't know. Like there are a lot of
It's not just policy. I mean, she's interested in policy, certainly, but just the idea of scientists being able to talk. It's certainly for this sort of thing. There's not a lot of but other people are getting calls from all sorts of times.
Yeah, that's actually true. Yeah, so if you think of like our understanding of
and she's got a lot of experience. But also, she came across. I've heard her give a couple of talks. She came across as really sincere and genuine.
yeah, so quasars are
I think if you contact her and ask her for some kind of advice, input, how you can improve your program.
Yeah, that's awesome.
Really think she would. I really think, at least in addition, I mean, I can't say how much time she has.
Well, no, that's you have asked here as well questions.
So from the theory of general relativity, we know that it's a ring. So that's exactly what we should I show you. So it should be a circle, it should be a circle, and it does it should be we don't know. Yeah, so
someone's giving a series of talks on science. I think Fred knows the news and I think it started. So
yeah. It's actually two women that used to
So I'm
So I guess to be more rigid.
I think the science of the interest of the audience is very so.
No. Two black holes.
yeah, for sure.
Yeah, it's still not the yeah, because we created the wrong it's two things yeah, you could have gravitational waves from the magnet, so they're actually supposed to have very, very so like around the yeah, it's also very weak, but it's also
Yeah, so it's not really.
yeah, because the interferometry is sensitive. No, there's no way to see the problem. But maybe like when it's so even if
it's very active. So that's like the weather would look like a flat spaceship. You have to wait till the universe is close to zero. We can ask after that. We can ask after that.
All right, keep that question. Oh yeah.
So for a black hole, only know it can have one. So that's really
All right, thanks for sticking with us and finishing all the snacks. That's excellent. So now we have one more speaker and then the demos afterwards. So take it away.
Thanks, great. So we've made it to our last stop in our voyage to discover the source of cosmic signals in our universe. And during this stop, I'm going to try to introduce one last astrophysical object called a blazar. Now, my name is Nicolo. I'm a second-year PhD student in physics at Harvard, and my research interests include cosmology and particle physics, where cosmology is the study of the entire universe at very large scales of time and distance. And then particle physics is the study of matter and interactions at the level of particles, where particles are things that we can't break down any further, just like electrons are particles. And then we said astrophysics a few times, so I'll go ahead and say what I think astrophysics is, where cosmology studies the whole universe at large scales of time and distance. I think astrophysics is more concerned with looking at specific objects in the universe and learning how the physics of those objects work. So I really have three goals in my presentation. The first goal is to introduce a really exciting event that happened last year and try and help you to understand why we think it's so exciting. The second goal is to introduce the source of that event, the blazar itself, and get an intuition for how the blazar works. And then my third goal is really to give you a kind of glimpse into one technique that we use when we do physics. So kind of going about the process of doing physics itself. But before we do that, I think it will be useful to quickly look at what Zoe and Nicolo have already told us about neutron stars and black holes, where the underlying lesson is that when you take a lot of mass and you squish it down into a very small area, you get really intense gravitational effects near that volume. You squish everything down. And then those really intense gravitational effects produce interesting phenomena. In the case of the neutron stars, we saw gravitational waves. We see space and time actually get kind of bent because of these objects and how massive they are. And then in the case of the black holes, we get the black hole itself, which is an object whose gravity is so strong that we can't get anything out of it. It just sucks everything in. It doesn't let it go. So understanding that when we put a lot of mass in a small area, we get really strong effects. Keep that in mind because I'm going to use it to try and explain how this object called blazar works. And to do that, this is the outline of how I'd like to go about that. I'm going to show you this really exciting event that occurred last year, and then draw on our lessons of gravity to try and explain this object that we think caused this event. And then in doing that, ultimately we'll have a model for how these things work. And so when another event occurs, we can try and repeat this process and test how good our ideas were for explaining what was going on. And I put my outline in this strange circle shape because I think it kind of illustrates the process of doing science generally. We make an observation, and we try and explain that observation using all the knowledge that we've acquired to date, and then maybe add a few new pieces to explain the things that we couldn't, and then we wait for another observation to test this new bit that we've added. And by doing this over and over again, we get to knowing everything that we know today. So without further ado, I will show you the event itself. Somewhere out in space, there's this giant rotating disk of stuff, and this is the quasar. And out of each end of the quasar is a jet of other stuff coming out. If we take a look inside of the jet, we see that it's actually made up of other things, different kinds of particles. Here, some look white, some look purple, and I know they were pointed towards the Earth, but that's okay because we're very far away, and so we only feel a little bit of the energy from that jet. And what you're seeing here are 3 different detectors that we have already built on the Earth to look at the different components of what's inside of that jet. And so on the far left, this is a representation of a detector called an ice cube. And what an ice cube does is it tries to look for particles called neutrinos. Now, all that you need to know about neutrinos are that they're elementary particles, just like electrons, so we can't break them down any further. And they have this weird property where they don't like to interact with matter. So if we wanted to see a neutrino, it means we need a lot of matter to do that. And so why is ice cube called ice cube is because ice cube itself is made out of the ice in Antarctica. It's a 1 kilometer by 1 kilometer by 1 kilometer block of ice that is laced with detectors that just wait for a neutrino to interact with that ice and then find out how much energy it had and where it came from. These other 2 telescopes are looking at light. They're just looking at really high energy light. So I'm going to come back to this event later on, but you can keep this in mind as we go forward, as we try to explain what the object that caused all this was. What is a quasar? And to do that, I want to once again bring up gravity. And think about how we're familiar with gravity in the most basic sense. And that is that gravity tends to have this effect that makes things be attracted to each other. You see all these little blue dots that are orbiting each other, or their trajectories are being bent because they're attracted due to the gravitational effects to the other blue dots around them. But what's really incredible about these little blue dots is that they can be anything. These could be planets, these could be black holes. They can also just be particles just floating out in space. The point I'm trying to make is the laws of physics work at many scales. That's why we call them a law. We say something is a law because it's really just a rule that we find works in a very vast array of situations. And that doesn't mean we think that laws are unbreakable, and we'd be really excited to find that one of our laws doesn't work. But my point is that in the case of gravity, we're very familiar with using gravity to describe why something like the moon orbits the Earth. But what's incredible is that we can go up to objects like black holes and neutron stars that are thousands and thousands of times more massive than the Earth and the moon, and find that we can predict their orbits using the same exact rules. So that's really cool. And we can continue this game. We can continue looking at examples of how gravity binds objects into orbits. And like Nicolo said, why don't we go floating off to space every time we take a step or go down or pop off something? And that's because the Earth has bound us to its surface gravitation because it's so massive. The same situation is why the Earth and the Moon are bound in orbit, and why the Sun is bound the sun and the Earth are balanced in orbit. And the sun is in fact so massive with respect to all of the planets that all of the planets will just more or less orbit the sun. Some doesn't really move around that much. And when we have a system like this, we call it a solar system. But we can go one step further and think of a really, really massive object that stars themselves would want to orbit around. And Zoe talked to us about how there's different kinds of black holes, and some of them are supermassive. And so it's these supermassive black holes that tend to bind lots of different stars and orbits around them. When we have a system like this, we call it a galaxy. And if you have believed me up to this point, then you might also believe me when I say that we are in fact in a galaxy, the Milky Way galaxy. And you might be familiar with the picture on the left, which you might be able to witness yourself, maybe if you went outside on a very dark night with a camera that has a long exposure and took a picture. You can see something, just like this. And another picture of the Milky Way galaxy is this one on the right, where instead of being from inside the galaxy, taking it from very far away from the galaxy. And what you see here is this giant swirling disk of stuff. And in the middle, it's really bright. And I'm going to tell you, in the very middle, even though you might not believe me because we call black holes black, there's a black hole there. And it's a supermassive black hole. And just like you're familiar with the concept of a year being how long it takes for the Earth to go around the sun, there's an identical concept for galaxies, which is a galactic year, which is how long it takes our solar system to go all the way around the black hole in the middle of our galaxy. That time is, I think, 250 million years. So it's much longer than the normal year. But why am I even talking about galaxies and the Milky Way in particular? We're trying to learn about quasars, and the reason I'm doing this is because quasars are a type of galaxy, just a special type of galaxy. It has a bunch of weird stuff going on near the middle. We see this jet of other stuff coming out. So there's something interesting happening near the middle of a galaxy that makes it a quasar. And so I want to try and build some intuition with you to understand, to try and come up with a good guess of what's going on near the middle of the black hole. And to do that, I want to go to another very basic, or not basic, but another concept that we're familiar with in everyday life, and it's called angular momentum. Angular momentum is really just a measure of objects moving in curved paths. Okay? And generally, I kind of introduced the concept of a law in physics already, and one thing that we find a lot of times when we call something a law is that it's usually associated with some quantity being conserved. So we find that if there's something, whether it's charge or mass, or in this case angular momentum, if it's conserved, then a lot of predictive results come out of making that assumption. So in the case of angular momentum, it depends on two things at least. And those are, if you have things moving in curved paths, there's a middle to that path. And so you can measure some distance, how far away is your object from the middle of that path, and how quickly is it moving around that middle of your path. And those two things have to, because we're conserving angular momentum, if you change one, the other thing has to change to compensate for that. And so figure skaters, I have pictures of figure skaters here, and that's because figure skaters take advantage of the conservation of angular momentum all the time in order to do their performances. And that's because if they want to go faster, they'll move their limbs, they enter a spin, and they have their limbs spread out, and they tuck that in closer, they'll start to speed up. Let's look at that. Okay. So one more time, I'll just talk this time. Here she goes into her spin. She starts out low and spread out. And when she wants to speed up, she pulls her leg in, and she goes faster. So now, using that very, this little idea of conserving angular momentum, we can take a guess about how things change as we move closer to the center of our galaxy. And thinking about that galactic year that I talked about, it's 250 million years for us, we can ask, how does the galactic year change as we go closer towards the middle? Really, I'm asking, do things go around faster? Do they go around slower, or do they stay the same? Maybe faster? Maybe we were inspired by the video of our figure skater? That's right, yeah. In fact, yeah, things do go faster as we move closer towards, well, they go around faster as we move towards the middle of our galaxy. And we have seen things go so fast, in fact, that we can measure them. We can watch them go all the way around the galactic center. So there are stars that we've measured their galactic year to be a couple decades. A couple decades is a long time, but it's a lot shorter than 250 million years. So it's a big change. So Nicolo introduced us to another concept. Nicolo kind of started explaining to us that whenever things get hot, another thing that tends to happen is they give off light. And so now if we think about what's going on near the middle of our galaxy, again, we have things moving around very quickly, maybe they're hitting each other. I mean, these are things that are like stars that are still exploding and everything else. They're just near the middle of the galaxy now. And in addition, we've taken things that were originally spread out very far and pushed them down into a much smaller circle. So there's a lot more energy just involved in that space. And so there's these collisions and there's heating, and so we can use that idea to explain at least part of the reason why the middle of the galaxy looks bright, despite the fact that there's a black hole there. So you have all of this energy close together, and things are hot. But we still haven't gotten to it yet. We still don't have these things shooting out of either end of our galaxy. And to understand that, I want to bring up the idea of a magnet. Just like Nicolo's fridge magnets. Magnets have this tendency to attract or repel other magnets, or metal things. And if we wanted to understand how a magnet is affecting things around it, we have a few different tools. One of them we call field lines. So we can draw a picture of these lines around a magnet that are really just trying to illustrate how it affects other things around it. Another thing that we know is that whenever we take charged particles, things that have an electric charge, and we move them around in circles, it produces an effect that is identical to a magnet. So if I took a coil of wire, like this one, and I ran a current through it, that is, I made charges move through this wire, it would behave just like this magnet. And in fact, if I draw these magnetic field lines, they look identical. And now I put this picture of a blazar right next to the picture of the electromagnet and the picture of the magnet to hint at something that might be going on. And what I'm trying to hint at is things are very hot and they're moving fast through the center of this galaxy. And what else happens when things get really hot is they start to break apart. So if you had things like electrons and protons that were combined in something like an atom, they will start to break apart as you get really hot near the middle of the galaxy. So now you have all of these free charges moving around quickly in circles in the middle of the galaxy. And what do we say happens whenever we move charges in circles? They act like magnets. And so we can, in fact, draw what we think the magnetic field lines of the galaxy look like right near the center, right near the black hole. And it looks something like this. And once I have something with magnetic field lines, I can take like a charged particle, I can take an electron, I can throw it at the field lines, and what the field lines would tend to do is change the trajectory of that particle. And they generally will try to make that particle, in this case, follow these lines. So if by some process, the black hole maybe sucks some material off of this is the accretion disk, by the way. All this material revolving around the black hole, we call it an accretion disk. It sucked off the accretion disk by the black hole, and the magnetic field lines bend that path such that it happens to end up in this little area here, or this area down here. Then those particles will keep going that way. And the magnetic field lines will have the effect of holding them in place, so like a cage that the particles can't get out of. And so now, We have a blazar. Okay, so we have this stream of really energetic charged particles coming out of the middle of our galaxy. And in fact, this isn't quite a blazar yet. This is what we call a quasar. What makes it a blazar is something really technical. It has to be pointing towards the Earth. It's not that technical. It just has to be pointing towards us. And so this is a blazar. And for the more technical definition, that's something you might see in the papers. A blazar is an intense extragalactic radio optical X-ray, and in some cases gamma ray, and in some cases gamma ray sources characterized by relativistic jets of plasma flowing close to our line of sight. I'm going to read that one more time, but break it down a little bit. Intense, there's a lot of stuff. Extragalactic, it's not in our galaxy, Milky Way, it's somewhere else because it's its own galaxy. Radio, optical, X-ray, and in some cases gamma ray. This is all just words for different kinds of light, different kinds. Sources characterized by relativistic, things are moving really fast. Jets, we saw the jets. Of plasma, this was all the charges separated and really hot. Pointing close to our line of sight, it's pointing towards here. That's a blazar. So, in fact, this event that happened last year was a blazar pointing towards the Earth, by definition. And what this picture on the left is trying to show you is there are two things inside of the blazar, two components that are important. One are neutrinos, and one are, well, the other component is light of generally really high energy. Neutrinos are generally very high energy. And why do those things exist? And the reason is because whenever we take things and accelerate them really quickly, maybe like right near the center of the black hole there, where we're shooting them up into that jet, it has the effect of producing these objects very often. And knowing that, we've built, not just that, but we built these telescopes for lots of reasons, but lots of signals only come in these forms of just light, different kinds of light, these different energies. And if we have these detectors in place on the Earth, then we can start looking at components of this beam. So what was the exciting event? Let's go think about it one more time, and I'll kind of narrate it as this plays. IceCube on September 22nd of last year saw an extremely high energetic neutrino inside of this giant block of ice. Okay, within 1 minute, IceCube said, "Oh, this is a really interesting event." Well, IceCube said this. This is a really interesting event. We determined that it came from this direction, and we think that the other telescopes might be interested in looking that way also. So they sent out an alert to all the other telescopes. There are dozens of these telescopes that look at light of just different energies all over the world. And all of those telescopes, over the course of several weeks, began pointing towards this blazar and seeing if they could see a signal that would match our guess of how a blazar would be emitting light. So they did that, and in fact, they did see something that looked very much like a blaze. So they all looked at their little bands of light. They determined where it was coming from, and then they all compared at the end. They said, "Oh, look, we're all pointing at the same spot, and I think it's a spot where we think the blazar is." So that's really exciting. But why is that really exciting? Why is seeing a neutrino at the same place where we see light that comes from a blazar exciting? We already knew blazars existed, right? The point is that IceCube had been looking at neutrinos for a long time and had been pinpointing places in the sky where we see these really high energy neutrino sources coming from, found, in fact, that they're all over the sky. This is kind of a projection of looking around the sky with IceCube and seeing that there's all these neutrino sources, but the other telescopes look and don't see anything. So why do we have all of these really intense neutrino sources, but no object there to explain where they're coming from? And so why this was so exciting is because it's the first time that we've seen something that can make neutrino energies that match these energies. And it's a blazar, and all these telescopes saw it, so we think it's there. Of course, there's always this game that has to be played when we do these major discoveries and observations, and that is, how do we know that this isn't just a coincidence? How do we know that there just happened to be a blazar there, and there just happened to be one of these neutrino sources in the same position. And this is enough for a whole other presentation, but needless to say, this is the reason why we need to see things lots of times, and why experiments need to run for long periods of time to be very sure that what we're seeing is not just a coincidence. That beyond any sort of doubt, there is these two events are correlated. They're very related to each other. And then just to illustrate just how many parties were involved in making this observation, I put up this map where all these dots are the circular ones are telescopes and observatories on the Earth, and up here you have some satellite-based observatories, and on the bottom you have IceCube, which is a neutrino observatory. All the other ones, except for this one in the middle here, they look at just light at different energies. And so we're kind of coming full circle now. So what did we find out? We found out kind of how a blazar forms, but we still don't know how exactly a blazar works. How exactly does that black hole suck the material off the accretion disk and shoot it out into the jet? I don't know. I don't think we know. And if we wanted to know better, we would have to have better probes of what's going on near the middle of the galaxy, like a blazar. And why is this so interesting? Also, is because I said that IceCube saw this neutrino, and it had an extremely high energy. I keep saying extremely high, but really it was hundreds of times more energetic than anything we can produce on Earth. So we have a machine called the Large Hadron Collider, it's at CERN, and it doesn't even get close to the energies of these particles. And so why is that so exciting is because if we have some physics that's locked away at very high energy levels, objects like blazars might be the only ways that we can probe what's going on at those scales. Or if not, if it's not the only way, it's at least one way. So with that said, I hope I also showed that this is a very collaborative and diverse experimental effort. I mean, this was dozens of satellites that each have, dozens of, hundreds of people on their teams. So with that said, that is what I had to say about blazars. And if you have any questions, I would be happy to try and answer them. Thank you.
So are there any particular reason why IceCube displays a South Pole, exactly like this ice there?
It's the ice. I mean, of course, I'm not on IceCube, and I only know IceCube based off the couple papers of theirs that I've read. But my understanding is you need clear ice that's stable and a lot of it. And there's more of that in the South Pole, and we also have some bases and whatnot that are on the South Pole. So I think those are the main motivating reasons for why I put IceCube on the South.
So it's not because of this particular position that's favorable for astronomy star. It's just that exactly.
No, actually, if I go back to this slide with the Earth, if you didn't want to use ice, maybe you could use water. It's not quite as clear, and things kind of change. So this is also a neutrino observatory, but it's in the ocean. It's literally in the ocean. They use the ocean as the detector. So they put these chains of detectors inside of the ocean. And they use the water. But I'm pretty sure it's a much smaller scale than IceCube is. So, yeah.
You said that neutrinos don't like to interact with outer matter. Is it that they don't? They can, but they often don't. Why?
You're right. So the question was, I said that neutrinos often don't interact with matter. Can they interact with matter? And yes, the answer is yes. They don't interact with matter often, but they do occasionally. And so that's why we need so much material to act as our detector. Why can't we just have a little screen that something hits and then we see if something happens to the screen? Yeah.
No, what I meant was why. Why don't they?
Why is a much longer explanation. With that said, I probably won't try and explain it now, but if you come talk to me after, I can take a shot at it. Okay, is that okay? Sorry. Yeah.
Getting back to the spin center of galaxy and near the beginning of the show, would that also have to do with dark matter?
Okay.
It's not just conservation of angular momentum.
You're right. You can't study for this talk, I guess. In fact, there are lots of things at play when we're considering how fast things are moving towards the center of our galaxy. So if we made the naive assumption that angular momentum was the only thing having an effect, we would be wrong. But we can still model how the galaxy would rotate based on that. So if we did that, we end up with some video that has something swirling. And now we can actually use our telescopes and look out at the things moving around and see if it matches our model. We did that. It doesn't. But it gets really close if we make the assumption that there's some giant cloud of matter that we just can't see that's present gravitational, having it has the same gravitational effect that we would expect. Then it matches our model. And so we do this, and what do we call this giant cloud of stuff that we can't see but has a gravitational effect, just like matter? We call it dark matter. So you're right. Yeah. The first, this was less than
Okay, I think in the interest of time, we'll let our speakers wrap up. So if you're interested in participating in the demo, you can head down. But first, we can give everyone a round of applause for a great. And before you leave, please try to fill out one of our feedback forms on the table out there.
Grab some flyers, fill out a survey, and come back to the demo if you want. Thanks.
Before you go, I did want to quickly summarize the entire talk.
Okay.
Just real quick,
Yes.
I'll be fast. Generally, we found that familiar concepts, gravity, magnetism, angular momentum, they become kind of strange when we take them to extreme conditions. And what's really exciting about observing gravitational waves, observing neutrino signals from astrophysical objects, is that this is the first time we're really doing that relative to all of history. I mean, for hundreds of years, we've only looked at light. That's it, all the way back to Galileo, his telescope. And now, within the past decade or so, we're seeing sources that are producing fundamentally different ways. And that's important because they give us insight into fundamentally different physics. And like I said, these quasars they produce, and all of these objects produce events that we can't possibly make on Earth. And so, in some sense, if we are interested in the physics associated with those extreme conditions, we can use nature as a lab. And that's an interesting idea to think about. The other point that we tried to drive across was that these discoveries, all of them are very huge, collaborative, diverse efforts with lots of people playing lots of different roles, whether that's scientists or engineer, technician, the politician who's getting the money to fund these experiments. These are all critical roles. And so if you think this stuff is important, you don't have to be a scientist to contribute. That certainly is one pathway that's open to everybody. And so with that said, I hope that we show that physics is an accessible topic that if you're interested in it, there are ways you can participate. That's what we have to say, so thank you.
I was thinking about that. I know. So, okay, first off. Or we can wait So, wait, where is this lab? I can like, oh, yeah, I can like meet him outside the like.
Yeah.
Okay. Yeah. Yeah, that's fine. Okay. I'm gonna put this in my wallet. That is somewhere where I will not forget it. Yeah. Oh, we should probably turn this off. Bye, internet.